Okay, now to understand motors and generators, we first just have to look at magnetic field. So an electrical field is where a charge, in other words, something that's given away or received an electron, experience a non-contact force. A non-contact force means nothing touches it and yet it's moving if the force is big enough. Okay, so and so a magnetic force is where a magnet experiences a non-contact force. Okay, now I must be honest with you, it's a very mysterious, for me, it's a very mysterious, like I understand, I suppose it's mysterious why positive charges attract negative charges and the same charges, like it is a weird concept. Well, not weird, just why? It's a good question. But magnets, like my wife was laughing at me the other day because I was just sitting with these two magnets and it just amazed me like how they work. It's fascinating. So anyway, but so what happens in some materials is they've got these small, I can't remember what they call them now, these small little patches, and I think this is also theory, okay, of little magnetic fields. But these magnetic fields are all in random directions. Okay, so and this is now only in metals. Okay, they're all just in random directions. But what you could do in a metal is you could magnetize that metal, and what you're then, and so when they're all in different directions, each one of them have a little bit of a magnetic attraction, like it's got a magnetic field around it. But the net magnetic field, because this one is in this direction, this one is in that direction, this one is maybe in this direction, this one is in that direction, the net electric field in the end cancels each other out. But what you could do by taking another strong magnet and pulling it over a metal, so if you take a strong metal and you brush it over what's that thing called? A nail, a metal nail. Then you magnetize it, because what you're doing is that strong magnet is now pulling these things because of its magnetic ability. It's pulling all of these little patterns to be in the same direction, resulting in their magnetic fields, just like we had E net E1 plus E2. Now if these are in different directions, they work against each other, and there's a lot of them, so but eventually the net is zero. But if they're all in the same direction, they work with each other, causing a magnetic field in the whole substance. Now so I'm just going to look at magnets in general. So a magnet in general will have this very interesting property that the one side of the magnet is now called north. It's nothing specific, it's just called north because the Earth itself also has a magnetic field. And I think the theory is that it's because of the friction between the core of the Earth and the crust of the Earth, causing friction and then causing a magnetic field in the metals that's in there. And so the magnetic field, the Earth's magnetic field, if this is the Earth magnetic field goes from the north to the south. It makes these magnetic field patterns, and it's a phenomenal thing, because if it wasn't for this magnetic field is actually from dangerous rays coming from the sun is pushed away by this magnetic field. But if it wasn't for that, there wouldn't be life on Earth. So there's, for example, some planets that don't have a magnetic field, and even though they're further away from the sun, the rays from the sun would harm life on that planet because there's no magnetic field pushing away the photons coming from from the sun, harmful photons. So a magnet. So the one is called north and the other one south because in the magnetic field of the Earth, they would line up with the magnetic field of the Earth, so that the one side of a magnet will point north and the other side of the magnet will point south. So that's why the one is called north and the other one south. And we find then that the field lines, the magnetic field lines, go from north to south. And since a magnet will always have one side north and the other side south, any force pushing away at this point will be attracted by that. So if there's a force going up here, it's being attracted there, so it has the same effect as having a Q1, a positive charge and a negative charge there. And that is why magnetic patterns will look like would look like that. And again, they don't cross each other. Okay. And it also then depends on how strong it is with a mirror pattern at the bottom. Okay. So a magnet by itself will have patterns like this, and then okay. But the next thing that can, but another thing that we can have is we can have one magnet here, for example. So this is not the whole magnet, just the one side that's positive, and I could have another one here, not positive, it's north, and another one that's north. Okay, and these ones will have the same effect as two same charges. So it will have those patterns that go like that. Okay. But if I have one here that looks like this, and I'm just showing this because it helps to understand motors and generators. If they are the same, then the field pattern goes like that. So in other words, similar to when we have a positive and a negative charge, electrical fields. Okay, but then something interesting happened, something that Faraday discovered, and I remember, I used to know the story, I can't remember the story anymore, but it is quite interesting. Faraday discovered that when you move, if I have a piece of wire here, and in this piece of wire I'm measuring the current, there's no source for energy. Okay. So what will the current reading be? Zero. There's no flow of electrons. But he saw that if you take a magnet, okay, and you move the magnet perpendicular, so not in the same direction, but perpendicular to the, so up and down in this case, to the wire, electrons start moving in that wire. So there is some sort of relationship, and I'm sure they don't know. I tried last year to study this a lot, and I couldn't find if they know what the relationship is, but there is some relationship between electrical fields, which is caused by electrons being traded, and magnetic fields, which is these ferro, I can't remember what they call them, but these ferro patches on metals. And when the one is pushed over the other one, it causes then, at a perpendicular, it causes, if I move it in the same direction, there's no effect. And so that's the one thing that they discovered. The other thing that he discovered is that if I had a current flowing through a wire, then around that wire appears a magnetic field around. So if a current is flowing through, then around the wire appears a magnetic field. And if I were to draw the magnetic field lines, they would be these concentric circles around it, and the further away I go, just the weaker that magnetic field is. So for example, if I were to put some metal filings on the table, and I would put this wire on that metal filings, it will actually pick it up. Okay, meaning that there's some magnetic field in here as well, and the direction of this magnetic field is also, remember, magnetic fields are vectors. The direction depends on the current, and so there's the right-hand rule that you can use to determine in which direction it goes. So your thumb points in that direction of the current, not the electron flow, but the current. So if you use your right hand, you have your thumb pointing in the direction of the current, and then your fingers will curl in the direction of the magnetic field. So these magnetic fields go in this direction. Does that make sense? Okay, now with these two facts working together, we can then create motors and generators, because in a generator is when I use kinetic energy and I convert kinetic energy into electric energy. So a generator creates energy. Well, we know much about generators in load shedding days, while in a motor, what I'm doing is I'm using electric energy and converting that into kinetic energy. Okay, so which principle will I use for which? The principle that when I move a magnet over a magnetic field, a magnet over a wire at a perpendicular distance, it creates a current. That's obviously a generator. So somehow I'm going to move a magnet over a conductive material, or I'm going to move the conductive material. It doesn't matter, as long as the magnetic field produced by this cuts perpendicularly with the wire. And in motors, we're going to say, well, if an electric current produces a magnetic field and a magnet pushes away another magnet, okay, or can push away or attract another magnet, then I can cause a force using electricity. Does that make sense? So this is then how it works. So I'll start with motors. If I had or in a motor, you will find that you will have a looped conductor, and let's say our current is passing in that direction. So if my current is passing in that direction, then I need to know in what direction is my... So look at that, use the right hand rule and tell me, is the magnetic field clockwise or anti-clockwise on there? So you use your right hand rule, and you can see they're going clockwise. No, that's anti-clockwise. Anti-clockwise. So if I was looking at this from the back, in other words, if I were to cut it in half, then this would be the wire that flows away from me, and a wire that flows away from me, it's almost like I'm looking at the back of an arrow. Okay, and then this is the wire that flows towards me, and then I look at the arrowhead. So if it's flowing away from me, I'll use my right hand. It is clockwise. Why? Yeah, sorry, you guys were right. It is clockwise. It's my sketch that's dodgy. Okay, it is clockwise. Okay, so in other words, I put my thumb facing my right thumb facing away from me, and then I see my fingers curl clockwise direction. Okay, so if my right thumb faces away from me, then my fingers are going clockwise. Okay, that's an ugly hand. Okay, and so this one goes in that direction. This one is obviously in the opposite direction, flowing towards me. Now if I put this between two magnets, so let's say we have north on this side and south on this side, so I just draw my north and south up here, a little bit away. Then notice this is a magnetic field. There's also now magnetic field lines going from here to there. From north to south. Now remember, when the two arrows point towards each other, they will push each other away. When the two arrows are pointing in the same direction, they're attracting each other. Now at this point, this one is going up, and this one is up, and on that point it's up. So let's just quickly see at this point, and this one is pushing forward, so at this point it is pushing it in that direction. Can you see it? And here at this point both of them are in the same direction. Here this one is also up, and this one is towards, and it's pushing it in that direction. That doesn't make sense. Let me just quickly look at my sketch. Okay, so let's rather work on this sketch. It's prettier than I can draw them. Okay, so again notice my this, can you guys see the picture that I'm looking at, that at this thing, but directly from behind, so that I'm seeing this current flowing away from me and this field current flowing towards me. Can you see that in this diagram here, for example? Okay, so forget about the slip ring and the rest of the things. Just consider the points now. So it's technically going here, around here, and then it's coming back and then connected to the slip ring. This is just perfectly from behind. Okay. So here, as you can see, if you point your thumb towards you, okay, as that dot indicates, then you're going in a clockwise direction. So here it is clockwise, here it is anti-clockwise because it's going away. Now I want to show you here that when the as the lines are coming down, notice that when they coming down, this one these two lines are in opposite. Do you see? So as it's coming down here, it's in opposite direction to this one. You see? So this one is pointing towards and that one is pointing towards. So if I draw a line between here and there, the lines would be opposing the line that I've drawn there. Do you understand? So if I'm connecting this with a straight line and I'm pointing an arrow, you can see the arrows are pointing against me, which means at this point it is being pushed in this direction. Okay? Away from north. For this one, if I connected this with a straight line and I go from here to there, notice that now the arrows is in the same direction as me. Notice I'm going towards S and the field lines are going towards S. Here I'm pointing away from north, but these ones are pointing towards north. You see, so this one is pushing away and this one is attracting. So if this one is pushing away and this one is attracting, then there will be a force in towards S. So this one is pulled towards here. The same happens here. Here, if I connect north to there, okay, my field lines are again opposing me. But that means it should push it away. When I connect these two, I'm opposing the field lines. Let me just see, because it depends on where you're looking at it from. Okay, let's just look at the one coming towards us for now. Okay, again, as it's being pushed more towards there, now when it gets to this point, then once again, it is being attracted by this one because the field lines that's closer are in the same direction as these field lines. So it's being attracted there. The same here, the field lines that are closer is in the same direction. Yeah, that's why it's being attracted. The field lines here are in the same direction, so it's being attracted. The field lines here are in the same direction, so it's being attracted. There, I've got it now. Okay, same thing here. Until it happens that I'm halfway there. Now, the problem when I'm halfway there is now some of the field lines, these field lines here at the top, notice they're in the opposite direction. So we should push away, but at the bottom they're in the same direction. They're going towards S, and here they're going away from S. Same on this side. So if I were to start a motor in this position, it won't go, because there's not an upward or downward. Well, there is an upwards and a downwards push at the same time. Okay, so it won't move. But because it was coming from the top, it had already some momentum once it got here. So it doesn't just stop, but it passes that point. The moment it passes that point, we're at that position. Now notice again that the field lines towards the center is pointing away in opposite directions. So now this one is being pushed away. The field line here is going towards the center, is in opposite direction because they're going towards north, and so they're being pushed away, and that's why it's being pushed downwards. So again, and this will happen all the way up to the bottom. Once I get to the bottom, to this 90-degree angle, once I pass there, now there's an attractive force between the two ends until I reach the center again. So I'll look at this splittering in just a second. The problem is that, okay, the moment I pass, where was it? Okay, so far the whole time we've been looking at this top one. Let's just follow that one. The current is flowing towards me, flowing towards me, flowing towards me. There, so here now it's on that side and it's coming down, so it's coming down, it's coming down. Okay. The problem is here, once it passes this 90-degree here at the bottom, notice now what's the problem. Now, as my field lines are pointing, the field lines towards the center of this thing, they would have the strongest effect, but the field lines towards the center are now pointing towards north, while these ones are pointing away from north, so it's going to push it away again. So the moment it reaches this vertical position, now all of a sudden it was going in this direction, but the moment it passes that 90-degree angle there, north is pushing it away again to go back. So in order, so this thing went now from the top all the way around. From the top it went all the way around. Even here it had enough momentum, though there's not an upward or downward force, it had enough momentum to go down. But once it reaches the bottom, because S is pushing it away, the moment it wants to go towards north, north is now pushing it away as well. So now it will get stuck. And the way that we solve it is by changing the direction of the current. Because if at this point I can change the current to go away from me again, then I'll have this top picture again. I'll have this top picture. So if at this point I can change the current, now the current, so it's going in this direction, but if I can now change the current to go away from me, because this is now down here, and that's now where the slip rings come in. So notice what happens is that these are the two slip rings, and so here, and I just noted here at the bottom of the picture that the current is in the wrong direction. Current goes, electron flow goes from negative towards positive. Current goes from positive towards negative. So let's follow the current. The current here, as I go out, goes in here, goes through here, goes up here, and around here. Around, so the current is supposed to be going towards me in this line. So it's actually not the current that's in the wrong direction, it's the battery that's in the wrong direction. So the current is going towards me, and so if the current, that's now in this part here, in that part, if the current is going towards me, it means that the electrical fields are in anti-clockwise direction at this point. But let me just see, because this is pointing out here. Okay, so let's just follow the arrows. Let's just assume that the arrows are correct. Let's forget about what's happening on this side. Let's just follow the arrows. So if I know the current was going in that direction, then this is correct. Okay, that is correct. So notice at this point, in what direction will it experience a force? Personally, I think this sketch is wrong, because no, this is fine. Notice that at this point, the field lines that are at the top here, because this is it's now below at the bottom, so the field lines at the top are in the same direction, and so there's an attractive force. So that's why this thing is being pulled up. Okay, now as it's being pulled up, at some point, and now I hope this sketch will make sense, these are the slip rings. Okay, so here's what the current does. The current is going in the outside circuit is coming in here, it's making a connection here, and then it's coming there. It can't go there. There's a split. That's why it's called a split ring or slip ring. There's a split there. Okay, so it goes down here, then it flows into that loop. Okay, so it's flowing away from me, and then so here's the loop. Then it's coming back towards me and in here. Now, if this was just connected directly, so if this was just a direct connection like that, then the current will never, in the external circuit, will never change. Okay, it will just always be in the same direction. But that's when it happens, that when we come to this 90-degree angle here at the bottom, once we reach the 90-degree, when we come to this point, we want the current to change. So notice what the slip ring does. The slip ring, let's try and follow it here. Notice that the slip ring here the current comes in. No, this is wrong. That little arrow there is wrong. It must be connected on here at the bottom. The current comes in. Oh, you can't see. Okay, yeah, I know that one is just not a nice view. Okay, look here what happens. Here the current comes in, follows, goes out, in the outside loop, comes back here, comes in here, out there, there the current goes. So this one you just can't see the thin little arrow here. That's the arrow in the loop. Well, this is the circuit. So here the circuit comes, then it goes into the loop, moves away from me, out in the loop, comes towards me, and then just comes to the slip ring and goes back into the circuit. Okay. So now what happens at this point, same thing, the current comes in, the current is going in this direction, goes into the loop all the way. Okay, but now what happens is the moment that we pass, I didn't draw, the moment that it's at a vertical position, we split our current. Instead of now going from here to there, it is now going from here up there. Okay, it's changing the current's direction. So instead of going from here to there, it would now be going from here up in here. And remember, this is now the one, so if its current's coming from here up in here, this one will be flowing away from me. At this stage, this one is flowing towards me into that direction. But if I can just jump this little bit, my current would be coming in here, there, and then this one will be flowing away from me. Okay, and so that's what happens once it passes. Once it passes here in the middle, you'll see that's where I reach the gaps, but I still have some momentum coming from this side. So as I jump over that gap, all of a sudden I used to be connected, this one used to be connected to that top one. Look, this one used to be connected to the top one. Now the moment I come past here, now I'm connected to the bottom one. Okay, which means my current is going in here. From here, it looks like the currents are opposing, but they're really not. The current is coming in here. This is just showing that the current is flowing towards this line. And this would have been the case if it wasn't for the split ring, but because of the split ring, yeah, this one is still showing, because of the split ring, it changes the direction of the current to now flow away. So the current is flowing away, and because the current is now flowing away from it, you can again see now all of a sudden my field lines, instead of where they used to be like this one in the same direction from north to south, they're now in the opposite in the opposite direction. It used to be in the opposite direction, and now it was pushing it away, but because of that split ring, I've now jumped my current to go, instead of going from this side that way, it's now jumped to go from the other side. Okay, I'm sorry, I haven't taught this much, so I don't have my wording nice behind me. So the way in which you can determine the direction that a motor is turning is you can use your palm, your left hand. So this would be the left. For motors, we use the left hand rule. So what you'll do is with your palm is going to indicate the direction in which the wire is being pushed. So imagine the wire is lying on your palm with your thumb facing the direction of the current. So it's lying here. Now you put your fingers in the direction of the magnetic field. So for example, in this case, my palm, the back of my hand must be from north, and my fingers must point towards south. I lie I now take the wire in my hand and then let my thumb point in the direction. So if the current was flowing in this direction, I would have just done that. Okay, but my thumb is pointing the direction of the current, and then wherever my hand then pushes is the direction in which my motor will be turning. So for example, this one is therefore pushed upwards. Why? Because if I put this wire in my left hand with my fingers pointing in this direction, then the loop will be pushed up by my hand. While on this side, Okay, if I'm on this side, I have to put my hand downwards, because the current, if I follow the current, is now pointing towards me. So if the current is pointing towards me, my thumb is pointing towards me, my hand will be pushing down. So this side is being pushed up, that side is being pushed down. And as a result, this thing is turning itself in a clockwise direction. Okay, so let me get to the question in the question paper. Electrical motors are used in pumps, fans, and compressors. And guys, this is really it. It doesn't get much complicated, much more complicated than that. There's no calculations involved. It's literally just being able to find out in which direction does the motor turn. That's motors. Okay, and maybe being able to explain it. So here they say, what type of electrical motor? Is it an AC or a DC motor illustrated in the diagram? Now, I didn't say to you what AC or DC is. AC means my current changes time. So I had two ways in which I could change the current in this loop. One way of changing the current would be to just manually swap the battery around each time it gets there. Okay, now that's not really what you do, but that is what we call alternating current, is when the current that I'm supplying is changing direction every whatsoever. Okay, in alternating current, the current that you supply is changing that direction, so there's no slip ring necessary. So an alternating current motor is a motor that relies on the source of your power. Your electric source is alternating. A direct current means that the current that's being supplied is not changing direction, and that's what happens here. Okay, the current that's supplied is not changing direction. The change in direction in the loop is being caused by the split ring. So how do I know this is a DC motor? Okay, give a reason. Okay, because the split ring changes the current. You always need an alternating current. You don't get in your loop a direct current consistently, because the moment it reaches that 90 degree, then it stops being then it has to have a current in a different direction in order to continue to turn. So this is a DC current, a direct current, because the current that's being supplied is a direct current. And I know that because the split ring is what causes the change in current direction. Okay. If the loop turns in an anti-clockwise direction, so they tell me in what direction the loop turns, in what direction is the current in section AB? So in this part, is the current going towards me or away from me? Is it going from A to B or from B to A? Right only. So again, we'll take our left hand, we'll put the back of our hands from north, the front of our fingers towards south. Okay, so we're going in that direction, and now I must see what is happening to AB. Is AB being pushed up or being pushed down? It's being pushed down. So if it's being pushed down, direction is from B to A. Make sense? The next question, the motor in the diagram is changed to operate as a generator. So let me just give you quickly the principles. I'll try and keep it quick. The principle of a generator now works that in a similar way, but this time I'm going to start with my north and south. Okay, and this time the change in direction, or not change in direction, the turning is caused by me. I cause the thing to turn. And because I'm causing this thing to turn, I'm moving, in this case you can see here, here's my field pattern. And at this point here, I am pushing it up. So if this is my magnetic field, I'm causing my wire to move perpendicular through a magnetic field, which means I am causing a current to flow in here. Now here goes my magnetic field. So as I'm pushing it up here, and I'm not exactly sure about the direction, because here we use the right hand rule to determine direction. Oh, I do that again. Here I use the right hand rule to determine direction. So in other words, if I wanted to now find out in what direction the current will be going, so let me do that. If I am pushing it up or rotating it up, again this is a loop. It loops like this. Okay, so this is just my wire. Okay, and I'm now viewing it from this side, but this wire is connected to, let's say, a little light. Okay, this is not good enough. Okay, here's my wire. Again, they connected to a split ring, and this split ring is connected to a little light. Okay, and if there's a current, the light will shine. Okay, now these are called bushes. That's what connects the split ring to the external circuit, and there's my loop. So if I'm pushing this thing up, let's see in what direction will the current flow. So this time I use my right hand rule. Okay, if I'm pushing it up, I'm and my palm is from north to south. Okay, then what I'm doing is the current is going to be flowing towards me. So this one will be flowing towards me, and that one will be flowing away from me. Okay, now you'll notice that at this point I'm at a 90-degree angle with my magnetic field line. But if I turn it now enough so that I'm here at the top, we said that the current that I'm inducing, it's called inducing a current, was flowing towards me. I'm pushing it to the top. This one is flowing away from me. But notice here at the top, when I'm my magnetic field now, that's now assuming that these are two equal sized magnets. At the top, it is moving in this direction, and my magnetic field is also in that direction. So now I'm moving my wire in the same direction as my magnetic field. You get that? And what Faraday found is it's only when you move it in a perpendicular direction that you're causing a current. So at this point here, I have zero current. I have my 0 ampere. Okay, so in other words, and now I go further. Now the moment I come to this side, notice what happens once I pass this side. My current is away from me. So on this side, let's say I had a current on this side that's bigger than 0. On this side I measured my current bigger than 0. On this side my current will be on that if this was an ammeter, if that was an ammeter, as it's going towards this I might have a positive reading, but the moment I reach that top and I come down, I'll have a negative reading, because the moment I pass so again, I am pushing this thing, and I'm not pushing it left, right, left, right, left, right. I'm literally turning it. And what I do when I do that is I'm creating an alternating current. Because the moment I get to the top, Here I have my maximum current at this point, because that's when I'm at a maximum 90-degree angle. As I go more, I'm only cutting some. Here I'm cutting all of the magnetic fields at a 90-degree angle. At another point, I'm cutting less of the magnetic fields. That's why my current is decreasing. At the top here, I'm in line, going in the same direction as all the magnetic fields. That's why I have no current flowing. The moment I come down here, now I start cutting my magnetic fields, but I'm cutting down. At the other place, I was cutting up. And so when I'm cutting down, if I'm using my right-hand rule, okay, it's being pushed downwards, so my current is now flowing away from me. So at this point, my current was flowing towards me. Now my current is flowing away from me. So in the outside circuit, all of a sudden, my direction has changed. Okay, the direction of my current has changed, and that's now just in here. Okay, so what happens now is that if I were to plot over time my voltage, or my, it doesn't matter, I suppose voltage is the best thing to plot, and most common thing to plot. If, let me just quickly see something. What I did here, what I drew here was, even though my current changed, again with the slip ring in the outside circuit, that doesn't have an effect, because even though my current changes, I again jump to the other side where the current now used to come from. So again, the slip ring causes the current in the outside. So the current in the loop is still alternating, it's now changing current, but because of my split ring, in the outside current, I'm still producing a direct current. My current is still. However, okay, my voltage still goes from a high volts, if that's now assuming that I start at this point, okay, my voltage goes from a high volts down to 0. Okay, once I reach the top here. So it depends now how I measure my angle. Okay, if usually what we do is we start at this point. We say, okay, at this point, once I pass this point, I'm pushing up, so my current is coming towards me. Okay, so let's take this as 0 degrees. 0 degrees. That one is 90 degrees. That one is 180 degrees. 270 degrees, and this is 360 degrees. Okay, so if that's the case, let me just wipe that out. It's usually how we draw these graphs. If I start, then here at the bottom, I start at 0 degrees. But as I'm coming closer to where I will experience my maximum, cutting the maximum number of magnetic field lines. That would be at 90 degrees. So at 90 degrees, I will reach my maximum voltage. But then it will go down at 180 degrees, I will reach 0 voltage again. Now it just depends on what do I have here. I've got two options. Either I have split rings that look like this, which will jump the current each time, or I could have it could look like this. It's here's my circuit, here's my outside circuit, okay, with my load there. This one is connected here, and this one is connected here. Okay, so notice here, as this thing is turning, this is also just these rings. I can show you this picture that I have here. Okay, notice that this one is always, this side is always in contact with this side because of that circle. This is a bush, that one, that ring is always in contact with the same one. This one is always in contact with that bush. So if the current in this thing changes, since it's always in contact, the current in the outside circuit will change. Alternatively, we could then still have the split ring, okay, because the moment in the split ring, the moment that my current changes here at the top, I jump from going in this direction to going in this direction. Okay, so again, the split ring will mean that I am changing my alternating current. In this case, the split ring means I'm changing my alternating current into a direct current. And in the previous, in motor's example, it was exactly the same. I had a direct current coming in and it was alternating the current in the loop. Okay, so if it's an alternating current, because I know I'm measuring my voltage here, notice the current in here is always alternating. If there's no slip ring, the current in the outside circuit must also be alternating. And then it means sometimes my current is in the positive direction, other times my current is in the negative direction. So for a complete turn, sometimes I will have a positive voltmeter reading and sometimes I will have a negative voltmeter reading. The highest reading when I'm cutting at this 90-degree angle. Make sense? Okay. But if I had my split rings in there, the moment it comes here, my current changes direction. So instead of going negative, it changes direction so that it keeps my current, my voltage positive. And so it will look like that. Okay. Good. Now, the value of your, this is obviously your maximum voltage that you can get. And your maximum voltage or your minimum voltage, they're just in opposite directions. But so we only work with maximum voltage, but maximum and minimum is the same, they're just in opposite directions. Okay? But the average voltage that you would get is called the RMS. I must be honest, I can't remember what that stands for. It's called the root mean square. Okay, that's one way of finding the average value if the value follows the sine shape. Okay, so if it was a straight line, we would use average the way we usually use average. But once I follow a sine shape, then the average isn't anymore just taking half of the maximum. Okay, so that is, instead of taking half, we take the square root of that, which is less than half, more than half. Okay, so the root mean squared, that is kind of what what you can expect to get your voltage at. It will always change, but it's what you can bargain on. So, and that is just taking your maximum divided by the square root. Now I'll show you now why that's important. Okay, and by looking at the formulas. Now power is the amount of energy that you can convert into another energy every second. Okay, and the formula for power, when we're working with alternating current, okay, not just with alternating current, but with these fluctuating currents produced by a generator. So a generator doesn't give a consistent current, it gives this fluctuating between 0 and Vmax, 0 and Vmax, okay, is given by this formula. So the average power, so now you don't have a consistent power putting out, you have an average power that you put out. And notice that the average power that you put out is the volts times because remember, volts is how many joules I have per coulomb, and current is how many coulombs pass every second. So multiplying the joules per coulomb times the number of coulombs per second gives me the amount of joules I spend per second. Okay, let me show it mathematically. If volts is joules per coulomb and current is coulomb per second, then if I multiply these two values, the C's cancel out to give me joules per second. And that's exactly what power is. So if I want to know what is my average power that I spend, I will take the average voltage, which is now just the root mean square voltage, which is the average for that, times the average current. And again, the average current is calculated the exact same way. It's taking the maximum current that I get divided by the square root of 2. So we just need to do that because in this question, to go on with to answer these questions, the motor in the diagram is now changed to operate as a generator. So here they now say, okay, instead of this being a motor, it's now going to be a generator. Just looking at this, will this generator produce an AC current or a DC current? AC. The loop will always be AC. Okay. The question is, what is happening in here? DC. It's DC because of the split ring. This is AC the whole time, but the moment that split ring comes in, it changes. Whatever change happens in there just has no effect on the outside current. Or if it was a motor, the split ring will cause the direct current to change into an alternating current. So on what principles do generators operate? They change that principle is going from kinetic energy to electric energy. Okay. Draw a sketch graph of the potential difference versus time for this graph. So potential difference versus time for this thing is this graph. It just had to be a rough graph. Okay, but because it is a direct current, both of the loops are on top. Okay, and you got 2 marks, one for having the correct shape and one for having one at the top, another one at the top. Okay, the diagram below shows a dynamo attached to a wheel. Okay, when riding a bicycle, explain how a current is induced in a coil. And that's just where you give the Faraday's law, is that when a magnetic field cuts a conductive material at a 90-degree angle, a current is induced in the conductor. And as the wheel is turning, it is rotating. So you can see here, it is rotating the magnet around a coil. A coil is just wound up wires. So obviously the more wires there are, the more electrons are being moved. Okay, so as the wheel is rotating, it is rotating the magnet to pass through the coil, inducing current. Okay. Now here's the question where I just want to show you, this is as difficult as it gets, really. It's not difficult at all. What is the peak voltage that the source can deliver? So let's just read the question. In the circuit we have an AC source. So there's my source is an AC source, and it's indicated, do you see that? It's that alternating current sine wave. Okay, the source delivers an alternating voltage at an audio frequency to the speaker. Okay, and there's just an additional resistor in, so that whatever voltage is being supplied is being corrected for the speaker. What is the peak voltage that the source can deliver? So here we have that our RMS is 20 volts, and did I do it correct now? If I look at my formula, RMS is the max divided by the square root of 2. So in other words, VRMS is V max divided by the square root of 2. Now they have given us, in this question, the root mean squared voltage. So they've given us 20 is equal to V max over square root 2, and so I just multiply both sides with the square root of 2, and this gives you something like 28,228 volts or something like that. Is it 28.28? Okay. So that's the maximum voltage that can be supplied. Okay. Calculate the average power delivered by the speaker. Okay, so remember what we said. Power, average power is equal to the average RMS times the average volts times the average current. Okay, so first I need to go and find the average current. I've got average volts, but be careful now. Okay, if this thing counts 6 marks, it's definitely not finding just the average current, but let's find the average current. Okay, so average current is simply your average volts divided by, you can't have average resistance, you just your resistance. Okay, so in our case it's 20 divided by our average resistance here. Our resistance here is 9.4, and 12.6 gives me 22. Is it? Yes, 22 divided by 22. So that is 20 divided by 22 gives me 0.099 0.909. If there's nothing in front of the comma, I like to round to at least 3 decimal places. But this one I'm not going to round because it's not what they asked me. They didn't ask me for that, they asked me for power, so I'm only going to round in my final answer. Okay. The next thing, guys, just notice what's important here. They ask, calculate the average power delivered to the speaker. So I need to know what was the current that the speaker gets, and the speaker gets the whole current because he's in series. But the speaker doesn't get all of the energy. The energy is being reduced by this, so he doesn't get the whole 20 volts RMS. We must first go and calculate how much voltage does he get, and how much voltage does he get. Okay, he gets the whole current times his resistance. So 0.0909 what times his voltage is 12,6. And so the volts that he gets is 11.4545, etc., etc., etc. Again, that's not my, I'm not going to round because that's not my question. But now I know what is the average power that is used or expended at the speaker is this 11,4545, etc. times 0.90909, etc. So times it's roughly 1,04 watts. Okay, understand? So again, it seems like most people thought it was easier than that. They just took RM, worked out total current and just substituted that. No, be very careful. They could say what is the average power delivered by the source, and yes, then it is the source, the AC source is giving this much, but they're asking what is it delivered to the speaker. Then it's about, well, how much energy is the speaker using per coulomb, and how many coulombs is he getting every second. In other words, the voltage and the current at that point. Okay. Alternating current is generated at power stations. Name 2 advantages of AC transmission over long distances. Well, there's various advantages. One advantage, for example, is you saw how easy it is to create alternating current, because if we go back here to my diagram here, notice that the two rings are in contact the whole time. Okay, so there's no jump of the current. Now if you are generating high voltages and you're using a split ring, each time you jump that current, there's a spark, which means it damages your split rings. While here, there's no disconnection. So the split ring creates DC current, and DC current causes damages on those split rings. So it's more costly. So it's more cost effective to do alternating current. Alternating current also, if I have alternating current, it's easy to then change from kinetic energy, from electric energy to kinetic energy, because I already have my alternating current. So I don't need a split ring in my motor to turn my motor. Okay, so it's also easier to transform. So that's one thing, and it's and because you have alternating current, if you have DC current, high DC currents, your resistance, not your resistance, your wires have to be withstand much more power, because now you've got electrons going up, a whole lot of electrons going in the same direction the whole time, causing this thing to heat up a lot. I think that's the reason. Doesn't seem right, because yeah, but it's also over long distances. It's also you can carry higher currents, higher AC currents, alternating currents, than DC currents. So there's just a few, but there's a few more in the course as well. Cool. Any questions from you guys? So please do me a favor, go and practice past papers on these topics, and get to questions that you don't know how to answer and ask me, so that I can address them, because I can really not find difficult questions. This one was now, this number 6.1 is, but it's not difficult. Like, if you actually get, oh wait a minute, I just need to use the voltage for that. It's not complicated. It's just you have to keep your head on, so you read your question carefully. Okay, thanks guys. Sorry I went over a bit.